I'm Nathan Matias at Cornell University.
I'm Eric Pennington at Cornell University.
I'm Zenobia Chen at Princeton University.
As Amy Orban has described in her work on the cycle of technology panics, researchers often respond to public fears with studies that, when done well, evaluate the effects of a technology within the general population. We can think of many examples of this, including concerns about screen time, phone addiction, and mental health, as well as concerns about misinformation, recruitment to extremism, digital manipulation, concerns about censorship and chilling effects on freedom of expression. In all cases, researchers, policymakers, and the public wonder about the causal effects of some technology system on individual and collective human behavior, and follow up with studies to evaluate these effects. One powerful way researchers have addressed public concerns has been through community or citizen science, where the public gets involved in investigating questions of common interest, generating knowledge that advances science, improves communities, and holds power accountable. Volunteers now routinely alert researchers about possible problems, coordinate measurement, and also test interventions on the full range of issues we consider here at FACT, independently from the tech industry. But even when community scientists study the effects of technology interventions, we tend to focus on average treatment effects. These are useful to communities and policymakers who have questions about population average issues, as well as technology makers who are curious about the impact of their products on average. Yet, as Mazur and colleagues point out, it's common to have situations where technology does not have a measurable effect on average, but people on the margins experience large positive or negative effects, either because the technology engages in discrimination or because people's circumstances and contexts are different. In these situations of inequality, the large positive effects experienced by some might be counterbalanced by the large negative effects experienced by others, misleading decision makers that a technology or policy is benign. In 1953, the anti-eugenicist biostatistician Lancelot Hogben argued against what he called the tyranny of averages, arguing that researchers ought to develop knowledge that informs individual needs while also avoiding the overgeneralization he saw as central to the statistics behind eugenics. To address this tyranny of averages, Hogben formalized N-of-1 trials, randomized trials that are conducted by an individual person or community, anywhere we expect to see many repetitions of an intervention and significant variation in effects between people. Today, these trials have been adopted by people managing chronic illness, studies in sports psychology, and education. N-of-1 trials, in them, individuals randomly assign interventions to different parts of their life, such as different days of the week or different parts of their network, sometimes over hundreds of different interventions. They also take regular measurements and, just as with any experiment, estimate the treatment effect within their own life. These trials provide personalized causal estimates with strong external validity and can also be meta-analyzed for patterns in populations, so long as the basic conditions are met. Now, because coordinating N-of-1 trials for many participants requires significant logistical efforts, scientists have created institutions and software to administer them, starting with the Ontario Ministry of Health in the 1980s to today's mobile phone studies of pain. Software systems and human institutions coordinate studies, support reliable measurement, and communicate results to participants. This paper is a research infrastructure systems paper where we implement and evaluate a software system for N-of-1 trials. Now, this is a genre in computer science that uses the design of a software infrastructure as a form of intellectual inquiry in its own right for exploring important ideas about software, data, and society. These papers tend to outline a knowledge creation challenge, summarize key values, relate the history of attempts to overcome the challenge. But they also describe design considerations for anyone designing such a system, report on the design of that infrastructure, report on its use in an actual study, and conclude with lessons for the design and use of similar systems. And that's exactly what we do here with a system we call Conjecture.
In this paper, we outline design considerations that are especially important for software that supports N-of-1 trials, including research literacy, autonomy, personalization, research integrity, and participant interpretation. Using personalization as an example, imagine that a study requires the N of 1 participant to be reminded to perform a particular task every evening. Allowing the user to personalize a parameter to fit better into their own schedule may help ensure that that user successfully completes the trial. And although the implementation of these considerations like these may vary from system to system, they apply more generally to any software that supports N of 1 trials. We develop these considerations when designing Conjecture, software that supports people to conduct N of 1 trials in our own digital lives. The software supports every part of the process, enabling people to sign up and start a trial at any time, complete a study, and receive back results when the study is completed. As we describe in the paper, the Conjecture system has a range of components that include user-facing systems supported by general UX components with the details of the specific study constructed from a series of modules that handle common N of 1 trial elements like randomization, for example. The architecture was also designed so that in principle, it can support multiple study designs aside from the pilot study we use to exercise the system. For instance, although randomization component works as is, it can also be extended to support randomization schemes other than what we used on the pilot study in the paper, likewise with other components as well.
We used the Conjecture system to conduct the Gray Phone Challenge, where we addressed the question whether a grayscale screen can reduce users' screen time. We first used Twitter and Facebook to recruit participants into our study. Once a participant agreed to participate, they had to fill in a survey to set up a time when they will receive a message instructing them to change their screen color. We also collected data on their normal cell phone usage, whether they have been diagnosed with color blindness, as well as what sort of result they expect to get from this study. After completing the survey, we asked participants to install the Moment app, which is an app that collects data on screen time and number of unlocks. The reason we chose this app is that at the time of the study in 2018, this app didn't collect any user data to their server, and all the data was stored locally on the user's phone and was easily exportable. In the first week of the study, we assigned all the participants to the full color condition, and each day they would receive a daily message. And we used the data from the first week as our baseline data. After the first week, we instructed participants to email us their screen time and unlock in an email. And after the baseline week, the 4-week Gray Phone Challenge started. Each day, the participants received a message asking them to set their phone in either grayscale or full color. And the participants then have to adjust the color based on the instructions of the day, and then stick with that setting the whole day. At the end of the day, we messaged the participants and asked them to confirm whether they stuck with the assigned color condition all day. Once the study had concluded, each respondent or participant received an individualized report. We visualized the results using quantile dot plots. Because most people's screen time varied widely from day to day, we chose not to present them with point estimates of the difference in outcome variables between days with gray and color screens. Instead, we presented the distribution of average treatment effects estimated from a non-parametric bootstrap alongside with the resulting 95% confidence intervals. Additional to each participant's individualized report, we also presented a meta-analysis of all the participants in the study. We did so by showing the 95% confidence intervals of the average treatment effect of each participant and we broke down the data by whether the participant reported any color blindness.
So one of the outcomes of our study was to generate lessons for future N of 1 trials. And here's some of the things we found. First, N of 1 trials can actually, in addition to being successful and generating useful knowledge, they can identify heterogeneity of effects through meta-analysis. By having enough participants and knowing things about them, we're able to group them in ways that helped us observe that this particular intervention had different effects for colorblind participants than those people who did not report having color blindness. Similarly, another challenge we had was that statistical power is particularly difficult to predict. We don't necessarily know in advance what the variation in screen time, in this case, our outcome variable, was between individuals. So it was difficult to inform people in advance about sample sizes. And we think that future system design could incorporate some more automated power analysis to help guide people through that, that process of understanding how long the study could take. Another challenge we faced is that it's challenging to explain null results. On one hand, null results can relieve concerns, but they can't necessarily comprehensively disprove something. And so tech accountability researchers doing research on this issue and others, I think, collectively need to think of good ways to explain and help people understand the meaning of null results and their limitations. We also have some suggestions and findings for the conjecture system and for other N-of-1 trial systems. We did find that it's possible to support a significant number of people to go through this process all by their own and get results and make sense of them. But we did find some trade-offs, and particularly we found a trade-off between participant responsibility and study completion. A number of our participants reported that finishing the study was quite challenging. The steps were complex. And we think that the more agency you give people, the more difficult it might be. So there's a trade-off there in the personalization that you afford to participants. We also found this trade-off that has to do with study selection. On one hand, the highest value studies are ones that involve the most harm and maybe the most difficulty in managing research ethics. This particular study was a fairly low risk study. We were looking at screen time. And as a result, it was a lower stakes form of knowledge that people were gaining. And so we think the N-of-1 trials could be very valuable in much higher stakes contexts. But if we take them in that direction, we need to put more time and effort into developing the right ethics procedures. And so in general, we think that particularly for these behavioral and well-being studies, there's potential in considering human challenge trials where people take on things that they believe to be significant risks in order to study them better. But before we go there, we're going to need substantial more work on both the general ethics approaches and how to support those ethics through software design. If you're interested in learning more about the conjecture system, perhaps using it in your work, or want to talk to us about N-of-1 trials, do reach out. I'm available via email, and you can contact anyone in the team. Thanks for watching our video, and we look forward to our conversations.